Okay, so this P6 revision video is for atomic notation, isotopes, and alpha and beta decay equations. And what we're going to look at first of all is how to write down an atomic nucleus, because if we're going to do the equations for the decays, we need to know how to write these things down. So we're going to use carbon as our example, and on the left we've got a carbon atom. I've shown the electron shells here on the outside. We're not going to show these again in the video because we're talking about nuclear decay. The only changes that take place are in the nucleus. Chemistry is involved with the electrons in the electron shells, and we're talking about radioactive things here, so this is all happening in the nucleus. So you won't see these electron shells again. Now, what makes a carbon atom is the fact that it's got 6 protons. Every single carbon atom in the universe has got 6 protons. Because it's atomic number 6 in the periodic table. And this particular carbon atom also has 6 of these neutrons that are labelled N here. So when we write down this nucleus, what we do is we use the symbol C for carbon from the periodic table, and then the top number that we write down, and the top left relative to the C, is the mass number, so the total number of neutrons and protons, and that goes up here. Okay. And at the bottom we have the proton or atomic number, which is the total number of protons in the nucleus, which of course is, we've already said, is 6. Now, because every carbon atom has 6 protons, you will sometimes see this notation written with the 6 missed out, because the C tells you that it must be 6. And the other way you see these nuclei written down is that you see the full name of the element, so carbon, with the mass number written after it, so carbon 12. So those are the 2 ways in which you can write down the nucleus of an atom. So some practice now. If you after this, if you pause the video and try and do the same thing for these 3 nuclei, write them down in both versions of the notation, and then unpause and we'll go through the answers. Okay, so first one on the left hand side, we've got hydrogen here. And we have 1 proton and 0 neutrons. Okay, so the mass number and the proton number are both 1. The symbol is H, as we see in the brackets here. It's hydrogen 1. And then helium, we have 2 protons and 2 neutrons here, so the mass number is 2 plus 2, giving us 4. And the atomic number is just the number of protons, so 2, and we've got helium 4, the mass number written after the element's name. And the final one here is nitrogen, and like all nitrogen atoms we have 7 protons in the nucleus. This particular one has 8 neutrons, and so we get 7 plus 8 giving us 15 mass number in total, and a 7 at the bottom, so 15, 7N on nitrogen 15. Okay, so we need to appreciate that there are different forms of the same elements. There are different versions of the atomic nucleus for elements. So we're going to look at another example here, and this is an element with an atomic number 4, which is beryllium. So this first version of beryllium is the sort of most common version of beryllium, is 9,4 beryllium, 4 protons and 5 neutrons in the nucleus. But there are also these and other versions of beryllium as well. So again, you can just do some practice here. If you just pause the video and then try and write down the notation for these 2 beryllium nuclei as well, and we'll check when you unpause. Okay, so this beryllium on the left here, these different versions are called isotopes, and the isotopes of a particular element obviously all have the same number of protons, but the difference is the number of neutrons. So this first one here is going to be beryllium 10, because we have 1, 2, 3, 4, 5, 6 neutrons, giving us beryllium 10, and the second one here is again 4 protons, 3 neutrons this time, giving us beryllium 7. So they're all beryllium nuclei, but they are different isotopes of beryllium. Beryllium 9, beryllium 10, and beryllium 7. Okay, so most elements have several different isotopes. Some elements have many, many different isotopes. And the thing to remember about these as well is that usually there's only 1 stable version, occasionally a couple. So by stable, what we mean is the nucleus will remain as it is, unchanged. Okay, if we just leave beryllium 9 alone, the nuclei sit there, they will not decay. Okay, and the other 2 versions of beryllium here are unstable nuclei. So they are what we call radioactive. They will give out alpha, beta, gamma radiation, okay, in order to try and become stable. That's what radioactivity is. It's the nucleus giving something out in order to try and become more stable. So, a little bit about what causes things to be stable. For elements near the start of the periodic table, you need a roughly equal number of protons and neutrons. So you can see here the beryllium here hasn't got an exactly equal number, this beryllium 9, but they're close. If you start to have very unequal numbers, like 4 and 6, or 4 and 3, I suppose is not that far off, but in this case the beryllium is unstable, then you get an unstable nucleus. And the decays sort of try and push this back towards a roughly 1-to-1 ratio. When you get up the high end of the periodic table, so to heavier elements, then you need sort of extra neutrons to make the thing stable. So as we'll see later on, the stable isotopes of things towards the top end of the periodic table have more neutrons than protons. Okay. Right, so how do these nuclei try and become more stable? Well, there are 3 different ways they can decay. There's alpha decay, where the nucleus basically spits out this thing here called an alpha particle, which is also the same as a helium nucleus that we saw from before, 2 protons and 2 neutrons. And it has this Greek lowercase alpha for its symbol, and it has a mass of 4 and a charge of +2, and we can use the same notation as before for the alpha particle, because it has a mass number of 4 with 4 nucleons in total, 2 neutrons and 2 protons, and an atomic number of 2. And this, by the way, is what gives it the charge of +2. The neutrons, remember, have 0 charge, and the protons have a charge of +1. So 2 protons there will mean that the alpha particle has a charge of +2. The second way of decay that we need to know is a beta particle, and a beta particle is basically just a high energy electron. Okay, so the beta particle has a symbol of a Greek beta, okay, and it has a mass of nearly 0. The electron has a mass that is about 1/1800th of the mass of a proton or a neutron. So we say 0 because it's very close to 0, round it down. And hopefully we all know that the charge on an electron is -1. Now here's where we have to stretch the meaning of this notation a little bit. Remember I said to you before that the top number is the total number of protons and neutrons in the nucleus, and the bottom number is the total number of protons. Well, clearly an electron doesn't have any protons or neutrons, so if we stick strictly to that rule, it should be 0, 0. But what we've also seen is that the charge on a nucleus is the same as the number of protons. So what we do is, in order to make this notation useful, we kind of slightly change what we mean. We change the top number to be the mass again, keep it the mass actually, and the bottom number we now say is the charge. So because these match for the alpha particle, it's reasonable to say they're going to match for the beta. So you need to remember that alpha particles are 4, 2, and you need to remember that beta particles are 0, -1. Okay? And then the final sort of decay that we need to know about is the gamma ray. Now gamma rays are part of the electromagnetic spectrum. They are not sort of matter particles. They are photons. So they have a rest mass of 0 and a charge of 0. So the numbers for the gamma are just 0, 0. So what tends to happen when you get these nuclear decays is that the nucleus will decay either by alpha or beta. And then all the gamma ray does, the gamma ray won't change the structure of the nucleus. It just lets the nucleus lose some energy. So I'll explain that again when we look at the decay equations. But the gamma ray doesn't really change the structure of the nucleus. It just lets it lose energy. Whereas the alpha and beta actually change the nuclear structure. Okay, so let's look at these a couple of examples. First, starting with alpha particles. So, what does the alpha particle do to the nucleus? So we've got this nucleus here, 11,5 boron, and it undergoes alpha decay. You'll never be asked to work out which decay something undergoes without being given clues. So you're not going to be expected to remember that boron 11 undergoes alpha decay. The question will tell you that and ask you to work out the consequences, or it'll give you some information and ask you to work out that it's an alpha decay, and we'll see how that happens in a second. So, like we said, all that happens in alpha decay is that 2 protons and 2 neutrons, so a helium nucleus, splits off from the main nucleus. I've rearranged the remaining neutrons and protons here. Okay, so we started off with our boron nucleus and it split up to become an alpha particle here and a remaining nucleus. So I'm going to remove this remaining nucleus over to this side and redraw the original boron nucleus. So this on the left hand side now is what we started with, on the right hand side is what we end up with. So we use a similar sort of notation to chemical reactions, even though this is a nuclear reaction. We have this arrow notation, and we have our one thing that we started with on the left hand side and the products of the decay on the right hand side. So we need to be able to write these down, and we should have had enough practice at this. We know that that's 4,2 alpha, because that's the alpha particle. And this is 3,7, so that turns out to be lithium. Again, you don't get a periodic table in your physics exam, so they're never going to expect you to remember that lithium is atomic number 3. They will almost certainly tell you that it's lithium, but you will have to fill the numbers in, and we'll see when we practice this in a sec. So there's our example for alpha decay, and that's the same thing that happens in every alpha decay. Now, here is where the use of the numbers becomes really apparent, okay? If you look at the numbers, then if we take the numbers at the top, on the left-hand side of the arrow, we've got 11. On the right-hand side, we've got 7 and 4. So the numbers add up on both sides of the arrow to the same thing. 11 equals 7 plus 4. And what that's really representing when you think about what the numbers mean is that the mass is conserved. We're not losing or gaining any mass here in terms of total numbers of protons and neutrons. Okay, they're just being sort of split apart. Okay. And the same thing for the bottom number. We've got 5 on the left-hand side, 3 plus 2 on the right-hand side. And because, remember, we said that we're not just taking this as proton number now, we're also kind of treating it like charge. What we're really doing here is saying that electric charge is conserved. We can't make charges out of nowhere. We're just sort of moving the charges about. So whichever nuclear equation you end up doing, this rule is true for everything, okay? Even when you get to slightly more complicated ones like uranium fission in a nuclear reactor, the total number on the top on the left-hand side will equal the total numbers on the top on the right-hand side, and the same for the bottom numbers as well. So the mass number, same on both sides in total, the charges, same on both sides in total, okay? So we can use that fact to fill in gaps, okay, if we get given a series of questions. So here are some questions now, and what you need to do is to, and this is the sort of question you'll like to get in the exam, is to fill in the missing numbers in these nuclear decay equations, okay? So some of them have got the missing numbers on the right-hand side, some of them have got the missing numbers on the left-hand side. You've just got to remember the rule that the total at the top has to add up to the same on both sides of the arrow. So pause, and then we'll go through the answers to these once you've had a go. Okay, so the first one here, this uranium decay, we've got 238, so that's going to be 234 plus 4, giving us 238 back again, and 90 plus 2 to 92. 204 plus 4 to 208, 82 plus 2 to 84. On part C, obviously we're missing on the left-hand side, so this time we have to have 218 plus 4 gives us 222, 86 plus 2 gives us 88, and this last one, 228 plus 4 gives us 232, and 88 plus 2 gives us 90. This is literally just adding up, so provided you understand the rule, it really shouldn't be that tricky, hopefully. Okay, so that's alpha decay. Beta decay is slightly more complicated, because instead of the nucleus just sort of being ripped apart, what happens instead in beta decay, and we're going to focus on this neutron here, is that a neutron in the original nucleus, and here we're doing carbon-14, which is a radioactive isotope of carbon, a neutron in the original nucleus turns into a proton and spits out an electron in the process. Okay? If you think about that, makes sense. We've got a charge of 0 here for the neutron, and the product that we get is a charge of +1 for the proton and -1 for the electron, giving us 0 overall again. So again, I'm just going to do the same thing as we did last time. I'm going to move the nucleus that we produce over onto the right-hand side here and redraw the original nucleus on the left-hand side. And you can still see the difference. The only thing that's happened is the neutron's changed to a proton. Okay, so if we look at this, then the beta particle, remember, is 0 minus 1. And then what we've got here is our nuclear decay product, so we have 14 again. You note the total number of protons and neutrons hasn't changed in beta decay because all we're doing is swapping a neutron for a proton. But what has happened is that the atomic number has gone up by 1, because we've now got an extra proton from that neutron transforming. But again, if you look at it, no matter the fact it's a different decay, the conservation rules still work. 14 equals 14 plus 0, and the thing to be slightly careful about here is this bottom one is 6 is 7 plus minus 1. So remembering that adding a negative number is like subtracting. So 6 is 7 minus 1 is basically what we're saying. But the same rules. So provided you remember that the beta particle is 0 minus 1, this shouldn't be a problem. Okay, same thing again. Have a go at these. Remembering that the total's got to add up. Pause and we'll check them. Okay, so first one, 60 at the top, same number as on the left-hand side because of the 0 on the beta. And 28 minus 1 gives 27. Next one, 137 at the top, 56 minus 1 gives us 55. Number C, we've got 3 at the top, again, 2 minus 1 gives us 1. And D, we have 19 at the top, and 9 minus 1 gives us 8. So those are alpha and beta decay equations. And remember we said for the gammas, you could theoretically put as many gammas as you like on the end of these equations because given off, because the gamma is number 0, 0, so it won't affect this conservation rule. You can add 0 onto both of them and it makes no difference. And this is what happens in real life. The gammas only tend to come off after an alpha or beta decay, because if you think about it, if your nucleus has just spit out an alpha particle, the remaining nucleus is going to be vibrating around and has a lot of extra energy, and the way it loses that energy is by giving out gamma rays. So the gamma decays usually come after an alpha decay or a beta decay. Right, just some last questions to try, which is a mixture of alpha and beta decay, and some at the bottom here where you have to work out which type of decay you've got. So again, pause, and then I'll just quickly go through these so you can check you've got them right. Okay, so A, I'm just going to show you them. I don't think we need to explain any more. We've got enough of these sorted. I'll explain these ones down here a little bit more. B, there you go. C, there you go. D, E. Now, so here, what we need to do is we need to just look at the differences. So we don't know anything. There was a complete blank there. But your only choices for your decay are alpha or beta, and clearly the only one that fits here is alpha, because we have to remember that alpha is 4, 2. So 229 minus 225 gives us the 4, 90 minus 88 gives us the 2. And similarly, F here, we must have a 0 at the top and a minus 1 at the bottom, so that's got to be beta. And alpha for this one, and beta for this last one, okay? So again, just to be clear, you won't be expected to know which elements these are. They will either give you the element, or sometimes they will put an X to represent an unknown element. All you'll be asked to do is to fill in the numbers using the conservation laws. So hopefully that's helped you understand what alpha and beta decay do to the nucleus, a little bit about isotopes, and how to use these rules to write down alpha and beta decay equations.